In example 6, we're given a sales function. It tells us about the total sales of our company in millions of dollars t months from now. So we want to find s prime of t, s of 15, which is the original function, s of t evaluated at 15, and the derivative function evaluated at 15. So again, using Wolfram alpha to get these results, you should be able to find that the derivative is 9 over 2 times the square root of t plus 1. That the original function, s of t, evaluated at 15, should be 36, and the derivative function evaluated at 15 should be 9/8 or 1.125. In part B, we want to use those results that we just came up with to estimate the total sales after 16 months and then again after 17 months. So we want the total sales, s of 16, but rather than plugging 16 into that formula, into that function, we want to use these results to come up with that. So we can approximate that value as s of 15 plus s prime of 15. Because again, what this number is telling us is that after 15 months, total sales would be $36 million. The derivative function tells us what will happen if t increases by 1. So 1 month later, our sales should increase by a little over 1.1 million. So we're taking those two values, adding them together. That gives us an approximate result for s of 16. So in this case, after 16 months, we'll have approximately $37.125 million in sales. And then we can do the same thing for 17 months. To get our sales after 17 months, we can take this result that we already came up with and again add s prime of 15. So we take that 37.125, add what that increase should be if we increase the value for t by 1. So after 16 months, this is our approximate sales. 1 month later means we add that rate of change again. So this should give us a little over 38 million sales, 38.25 million sales. So in example 7, we're back to a regression problem. So we will go through all the steps with Wolfram alpha for this to demonstrate this problem. What we have is annual income from limousine production for these selected years. In part A, we want to let X represent the time in years since 1980. So that means our years column is our X variable, and Y represent the corresponding production. The one catch though is that X represents time in years since 1980, so we need to update these values. So in 1980, it was exactly 0 years since 1980. 1985 is 5 years later. 1990 is 10 years later. 1995 is 15 years later, and the year 2000 was 20 years after 1980. So what we want to do is type each of these into Wolfram alpha as XY pairs. Just to save time, I've already done that. So I've got 0, 2900, 5, 6500, and so on. And we're going to start off with this command cubic fit, because what we want to do is fit this data to a cubic regression equation. So we get our cubic regression equation, 5.47, because we're asked, let's see, because we'll probably typically round these to about 2 decimal places. So we call this 5.47, 167.71, and so on. So I'll flip back over and record that in a second, but we can click on this function to again save ourselves the trouble of retyping that. So we've got our regression function, which means we can just add derivative of in front to get the derivative of that function. Wolfram Alpha is going to go ahead and generate that output for us. 16.4x squared minus 335.428 plus 1307.62. Actually, let me go back and make a couple of modifications because the answers that I wrote down and I'm about to write down, I rounded these results to the nearest hundredth. So I'm going to look at each of these numbers and just round those to the nearest hundredth. So the first two don't need to change. This I rounded to 167.71, and this will round to 5.47. And we'll calculate that derivative one more time. So we don't get a big change to our result here, just a little bit of change. Some of these are now carried out to the hundredths decimal place, but just to match the answers that I've got pre-written down, I'm going to record here in a second. So rounded to the nearest hundredth, our cubic regression equation was 5.47 x cubed minus 167.71 x squared plus 1,307.62 x plus 3,014.29. So taking the derivative of that function, which with each of those numbers rounded to the hundredths place, our derivative function is 16.41 x squared minus 335.42 x plus 1,307.62. So now what we want to do is evaluate L of 11 and L prime of 11. So we could again do that using Wolfram Alpha. Evaluating the original function at x equals 11 would give us a result of 4,385.77, and L prime would give us a result of negative 396.39. So now what we want to do is interpret what these results mean. So the 11 here represents our number of years since 1980. So in the year 1991, which is 11 years later, the number of limousines produced is given to us by the original equation. So the number of limousines produced was 4,386, if we round that to the nearest whole number. And the number produced was decreasing since our rate of change is negative. It was decreasing by 396 limousines produced each year. So doing the same thing for L of 17 and L prime of 17, we would get a result of 3,649.75 and 347.97. So now we're talking about 17 years after 1980. So in 1997, the number of limousines produced was 3,650, and the number produced was, since now our derivative gives us a positive result, was increasing by 348 limousines per year. So when we're using Wolfram Alpha, the emphasis is going to be on providing interpretations for what these results mean. In this case, understanding the difference between the original function telling you about revenue, sales, costs, in this case limousine productions, and the derivative function telling you about how quickly that production level, revenue, cost, whatever it is we're considering, how quickly that's increasing or decreasing, and understanding that it's increasing or decreasing based off whether that result from our derivative function gives us a positive value or a negative value.